Modern condensing boiler systems offer high efficiency and precise control. Optimal performance depends on temperature sensing, flow control, and energy storage management. Let's explore how control, variable flow, and buffer tank sizing ensure an efficient, stable, and long-lasting condensing boiler system. Older systems controlled boilers using return water temperature, causing slower responses to load changes. This led to fluctuating space temperatures, comfort complaints, and cycling issues. Modern systems place the temperature sensor on the supply side for faster feedback and immediate response to heating demand. Condensing boilers are most efficient when return water temperature stays below 120 degrees Fahrenheit. Cooler return water increases condensation inside the heat exchanger, recovering latent heat from flue gases. Thus, as return temperature decreases, efficiency increases. The ideal control strategy anticipates load changes by monitoring flow rate, supply temperature, and return temperature. It modulates each boiler's firing rate to maintain the lowest possible level, as multiple boilers at low fire are more efficient than one at full fire. Older boiler designs avoided variable flow due to concerns about thermal shock. However, modern full condensing boilers feature robust stainless steel or aluminum heat exchangers that safely handle variable flow. This eliminates the need for mixing valves, constant primary flow loops, or high return temperatures. We can now design for variable flow, provided pumps and boilers operate within their rated flow ranges. Today, two main configurations are used: variable primary flow VPF and variable primary/variable secondary VP/VS. In a VPF system, a single set of pumps serves both boilers and the distribution system, with flow varying based on demand. ASHRAE 90.1 requires flow reduction when a boiler is off. This requires flow limiters at each boiler inlet to prevent overpumping. Two-way isolation valves stop flow through an idle boiler. Pump valve interlocks ensure no pump runs unless a valve is open, preventing deadheading. When a boiler shuts down, the pump runs briefly to remove residual heat, and the isolation valve closes after a short delay. Control logic must maintain minimum boiler flow during startup. It must also keep minimum pump flow for staging. Overall system flow must never drop below the manufacturer's specified minimum. A three-way valve can bypass flow when coils are closed, ensuring minimum flow during startup and shutdown. Now let's examine the variable primary/variable secondary configuration, often considered a top-tier approach. Each boiler has its own primary pump, and a separate secondary loop circulates through the building distribution. Both loops can vary flow independently. At low load, the secondary loop may meet demand with residual heat from the buffer tank, potentially eliminating the need for boilers or primary pumps to run. Since each boiler has its own pump, flow limiters and isolation valves are not required, automatically complying with ASHRAE standards. A buffer tank is often added between the loops, especially with low water volume boilers, to store BTUS, increase boiler runtime, and prevent short cycling. In the secondary loop, variable speed pumps operate based on differential pressure in the critical zone. A three-way bypass valve maintains minimum pump flow and directs excess water back to the buffer tank when zone valves close, preventing deadheading. The primary loop maintains a constant temperature rise across the boilers, while the secondary loop maintains constant differential pressure across building loads, working independently. A buffer tank is essential when the system's total water volume is insufficient to absorb excess heat, common in low-mass or modular systems. The buffer tank stores excess BTUS, extending boiler runtime and preventing short cycling. Proper sizing depends on the minimum desired runtime, usually 10 minutes. It also depends on the minimum boiler output in British thermal units per hour. The minimum system load in British thermal units per hour is another factor. Finally, the system delta T in degrees Fahrenheit is crucial. The formula uses constants 8.33 and 60 to calculate the required gallons of storage. This ensures smooth boiler operation without constant on-off cycling. Understanding the boiler supply delta T, the difference between start and stop temperatures, is critical for sequencing multiple boilers. A typical boiler delta T is around 12 degrees Fahrenheit. For a 180 degrees set point, it fires at 174 degrees Fahrenheit and cycles off at 186 degrees Fahrenheit. Modern boiler controllers use PID logic to manage this precisely, sensing supply and outdoor air temperatures to adjust firing rates smoothly. When load decreases and the secondary loop removes fewer BTUs, supply temperature rises, signaling the controller to reduce firing or shut down a boiler. This results in stable operation, longer component life, and higher seasonal efficiency. Recap: controlling on supply temperature provides faster response and better comfort. Keep return water below 120 degrees Fahrenheit for maximum condensing efficiency. Designed for variable flow as modern boilers handle it safely. Include flow limiters, isolation valves, and interlocks in VPF systems. Use dedicated pumps and buffer tanks for VP/VS designs to prevent short cycling. Maintain independent control of the primary and secondary loops. Proper buffer tank sizing ensures steady operation. Always tune boiler controls with PID logic for smooth modulation and sequencing. Applying these strategies creates a quiet, efficient, and reliable condensing boiler system across all load conditions.